The binomial distribution is a well-known distribution in and outside data science. However, have you heard of its lesser well-known cousin, the hypergeometric distribution? No? Well, in this video, I'm explaining to you exactly what it is. If you're new here, I'm Igor. I'm a data scientist living in London, and on this channel I give detailed tutorials about statistics, data science and machine learning. So if that sounds interesting, make sure you subscribe. Anyway, let's get into the video. So we will first begin with gaining some intuition behind what the hypergeometric distribution is. So the hypergeometric distribution measures the probability of k successes in n number of trials, a sample in this case, without replacement, given some information about the population. Now this may seem like a mouthful, but we'll go through an example in a second to make that really concrete and really simple to understand. So this is very similar to the binomial distribution. I've done a video on the binomial distribution. I'll link it somewhere on the screen here. But the one key difference is that it is sampling without replacement. And that changes how we approach the problem, because the probability of a success will then change every trial. Whereas in the binomial distribution, the probability of a success is fixed. So a really simple example to understand where we would apply the hypergeometric distribution is this. So let's say we want to determine the probability that we have drawn all 4 kings in a random sample of 20 cards from a deck. So in this case, we've got a deck of cards, 52. We've randomly taken 20 cards from that 52 deck. And what we want to know, what is the probability of that 20 cards containing all 4 kings? So that's an example where we're using the hypergeometric distribution. If we draw a king, the probability of drawing the subsequent king will be different from the first, as the population composition has changed. Like if we draw 1 card, we then have 51 cards left in the deck. And so you see how the probability of drawing a king each time will decrease, right? And because of that, the probability of a success is dynamic. It's changing. It's not fixed like it is for the binomial distribution. And that's kind of the key difference between the hypergeometric and the binomial distribution. Now, the theory behind it and the probability mass function looks like this. So there's kind of, there's 4 key elements, and x is a random variable here. So what you see here is that we want to know what is the probability of the number of successes we're after, where k is the total number of successes in the population. In this case, this would be 4 kings, right? And n is the number of trials, so just basically how many cards we take out. N is big N is the population size, and like I said, k, little k is the number of successes, big K is the total number of successes in the population. And if you're unfamiliar with this notation here, this is just the binomial coefficient notation written like this. So it all comes from the idea of combinatorics, and this is a factorial function. It's just saying how many combinations exist for A choose B. If you're unfamiliar with that, I'll link a blog in the description below that you can check out the ideas behind permutation and combinatorics and how this formula actually works and why the number of combinations is given as so we've shown on the screen here. Also, if you're interested in deriving this from first principles, I have linked it here. This whole presentation will also be linked in the description below, so you can check out that link if you're interested. But this is the main theory behind it, the whole PMF. It may look scary, but in reality it's quite simple. Once we know the numbers of, big and large n and k, then it's very simple to actually work out the probability of some problems like we showed in the previous slide. So let's now go back to the previous example we had. In that case, remember, we want to know what is the probability of drawing 4 kings in a random 20 card sample from a regular deck of cards. So if we go through that bit by bit and break down what we have in our problem. So a standard deck of cards has 52 cards, right? We were after 20, which is our sample. So it's little n equals 20. The total number of kings in the deck is 4, and we want 4 kings, right? So in this case, both big K, the total number of successes available is 4, because there's 4 kings, and we're after getting all 4 kings in our sample. And all we do those numbers, as you see on screen here, is that we plug them back in, and with that we get this outcome of 0.0179. So in other words, we're very unlikely to get the 4 kings out of that 20 card sample. Which makes sense, right? Because getting one king out of 52 is 1 divided by 52, and so that's a very small number. Like, what is that? Less than 0.02%, right? So in that, or less than 2%, I should say. And so you can see why this is even smaller, because getting 4 kings is very, very unlikely, right? And so it's very hard. You're assuming you're going to get all 4 from 20. Very unlikely, which so makes intuitive sense, this outcome. But I hope this problem makes sense to you. Again, it's pretty simple to understand. It's just understanding the problem we have and then framing it and understanding what each value in your problem is. And then it's just simply substituting that information back into the PMF that we showed in the previous slide. We can also have a distribution. So instead of drawing 4 kings, we can show what's the probability of 0, 1, 2, 3, 4 kings at that sample, and we can construct a distribution. So on the right here is the Python code. Again, this will be linked in the description below in my GitHub. But you see here, what we have is that I import this Hypergeom function from SciPyStats, which is the hypergeometric PMF I showed in the previous slide. We define our values. In this case, we know big N is 52, number of cards in a deck. Big K is 4, number of successes, so 4 kings. And N is our sample. And then we're going to iterate over all the possible number of successes. So we know we can have 0 to 4, well, in this case. Then we're simply going to call the PMF function on that information we provided and then plot the results. As you can see here, the most likely outcome is that we will draw 1 king, which kind of makes sense, right? Because we have 4 options, and so what 1 king is kind of like 1 in 13 chance, right? So 20, and so therefore 20 divided by 52 is kind of the closest approximation to 1 in 13. Similar, 2 is very similar as well, because 2 would be 1 out of 26. Yeah, 2 divided by 52. Really good maths there. And so you see 1 and 2 are very likely, and they're kind of very unlikely to get 0 or 3, and even less likely to get 4. And obviously in this case I've added 5, but obviously the probability of getting 5 kings is 0 because there's only 4 kings in the deck. So from this we can see that indeed our function is working appropriately, and we can see what the distribution looks like for the PMF. Let's now have a different example. In this example we're going to say, what is a number, from our 30 card sample, how many of those cards are spades or belong to the suit of spades? In this case, we can do a similar approach. We know we have 52 cards in our deck, so big N is 52. K, big K, number of successes. So the spades suit is exactly a quarter of the deck, so therefore there's exactly 13 spades cards inside the deck that we can possibly get. In this case, our sample size is 30. We're taking 30 cards out of the 52. We do the same thing where we iterate, or we get a list of all the possible successes. In this case, is 1 to 13, and then we plot the results like we did last time. As you see, we're actually really unlikely to get 0 spades in our deck, which is quite shocking, right? So we're saying we're very likely to have at least 1 spade in that 30 card sample that we take. Obviously, 14 is 0 because we can't get 14, but you see the peak is around kind of 8 and 7, which, if you think about it, makes sense. So we have a quarter of the deck is spades, right? And they're quite evenly distributed. So what we would expect is that a quarter of the 30 card sample would be the most likely to be spades. So a quarter of 30 is about 7.5, and you can see how the distribution is roughly between 7 and 8. So in the middle of them is 7.5. So you can see it kind of follows that sense that because we're evenly distributed, we assume the 30 card sample will have an even distribution of spades cards, which is really interesting to see, and that kind of meets or matches our intuition behind this type of problem. So I hope that makes sense. Again, the code will be attached in the description below, so if you want to play around with it, do whatever you want, then feel free to check it out. It will also build up your understanding behind the hypergeometric distribution and what it's trying to solve. Now, it's very useful going through those examples, but where is it really used, the hypergeometric distribution? So it touches a lot of fields. We've even used it in my role a few times in my job. So it's really used everywhere, and it can be applied in so many sectors. Obviously, going back to our card example, it can be used in calculating the probability of winning a hand in poker. In general, just gambling can be used in most like casino games. As you showed there, you can use cards, dice, things like that. It's also used in voting populations analysis. So, you know, we in voting population analysis, we normally take samples because we haven't got the whole population range. So we have a sample, population, you see how we can apply the hypergeometric distribution there. Again, quality control, the same idea of taking samples. And then also genetic variations within a population. So it really does touch so many fields. So if you're a data scientist or any form of like statistical professional, then I really recommend learning it because it may come in handy in your role without you even realizing it, or you may be able to apply it to a problem that you're stumped on, and it can solve that for you, which is really neat in most cases. So I hope you enjoyed this video. I've attached a blog that relates to this video in the description below, so feel free to check that out if you want to know more about the hypergeometric distribution. If you want to, I've got my other channels linked here, so obviously this YouTube channel, make sure you like and subscribe if you like this video and also want to learn more about statistics, data science and machine learning. A lot of the stuff here is linked to my GitHub, and you can also find me on Twitter. And I also write a newsletter, which is also linked in the description, every Monday, which is all about my thoughts and feelings as a data scientist and just some like insider tips. If you're interested in that, that's also linked in the description, like I said, so feel free to check that out. If you enjoyed this video, make sure you like, comment and subscribe, and I'll see you in the next one.